So here's what our plan for this week is going to look like. And you can see this if you look at the calendar. We're going to spend Monday, Tuesday, Wednesday talking about this topic. This is going to be one of your homework assignments for the chapter. We're going to do a large portion of it together in class. So you should be able to have something done on that. What I'm going to do over spring break is I'm going to give you a set of free responses to give you as a homework assignment. So usually we do 5 years worth of free responses. So instead of giving you a set of free responses while you're also trying to do the last chapter's worth of homework. Instead, I'm going to have you do a set of free responses. And I will take Thursday. If you look on the calendar, on Thursday, I'm going to hand out the free responses and give you some time to get started on them. So that's what we're going to do on Thursday. And then on Friday, I had done a Zoom meeting last Friday, and then I ran into technical difficulties. So I'm going to redo what I did last Friday. I'm going to do that again this coming Friday. So that is our plan for the next 2 weeks going forward. And then we will properly start our areas and volume stuff when we come back from break. Any questions on that before we go on to today's stuff? All right, let's do it. This is called L'Hôpital's rule. Most places you'll see it spelled this way. Sometimes you'll see it spelled like the word hospital. It just depends on where you're looking. But I believe the proper spelling is supposed to be this. But some places will spell it differently. Sometimes I spell it differently on different worksheets and stuff. Or I title things a little bit differently. But most of the time you'll see it spelled this way. Wikipedia says either way is fine. And as we know, that's the ultimate trustworthy source. So, going with that. All right. This rule is another technique for finding limits. I know we haven't talked about limits in a while, but this is another technique for finding limits. And this is a specific technique that works for what we call an indeterminate form. It's called that because we can't determine what the number is that the limit would be. So this is for simplifying to things like 0 over 0, infinity over infinity, 0 to the infinity power, things that you wouldn't be able to know what the number is. Basically, mixtures of zeros and infinities. If the form is not a mixture of zeros and infinities, then we can't use this rule. Not allowed. So if we get 0 over 5, well, then the limit is 0. Because 0 over 5 is 0. If we get 5 over 0, we have to use something else to find the limit, but 5 over 0 is not an indeterminate form. It would have to be, most of the time, you'll see it be 0 over 0. So you'll have a function on the top and the bottom, and the top when you plug it in is 0, and the bottom when you plug it in is 0. So here are the things that you need to check for in order to do L'Hôpital's rule for these limits. 3 things you need to check for, or 2 things you need to check for. we need to check for, number one, an indeterminate form. So do we have like a 0 over 0 or a 0 over infinity or something like that? And number two, we need to check that f and g are differentiable, which will also mean they're continuous. The reason we need to check if they're differentiable is because the theorem, the rule is going to involve taking a limit using derivatives. So if we're using derivatives, then we better be able to take the derivative. It better be differentiable. If those two things are true, if we have that indeterminate form and f and g are differentiable, so in other words, the top function that we have and the bottom function that we have are both differentiable, then we can find the limit of f prime of x over g prime of x. This is not quotient rule. This is not low d high minus high d low over square of what's below. This is, I'm just taking derivative of the top, and then separately I'm taking derivative of the bottom, and then evaluating the limit. So if you looked in your book, then this is the way you'd see it written. Suppose that f of a equals g of a equals 0. So in other words, a is a point that I'm trying to find the limit at. And I plug in into the function, and I find that I get something like 0 over 0. There's my indeterminate form. That f and g are differentiable. There's my differentiable. On an open interval containing a and g prime of x is not 0. So derivative of the bottom is not going to end up being 0. Then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. If the latter limit exists. So, in other words, I can do, I can take derivative of the top, derivative of the bottom, and do the limit there. Let me convince you that this works by doing a problem that we already know how to take the limit of. So let me do of x squared minus 5x plus 6. This is an extra example just to show you how this works. We're going to take it the way that we learned how to take it when we first did limits, and then we're going to do it with L'Hopital's rule as well. Now, method number one. This is the main method that we have to take a limit. So I want to review that with you because it's been months since we've done limits. So that's why we're doing this extra problem. So the way that we would usually do this is, first we would try direct substitution. And see if that works. We get 3 squared minus 5 times 3 plus 6 over 3 squared minus 2 times 3 minus 3. What happens? It's 0 over 0. That's my indeterminate form that tells me that I might be able to use this rule. The other condition is that f and g are differentiable. So in other words, that is x squared minus 5x plus 6 differentiable? Yeah, it's just polynomial. Is x squared minus 2x minus 3 differentiable? Yeah, it's a polynomial. So we can use this rule. But let's start by taking this limit the way that we usually would. So like I said, first we try direct substitution, and then we find 0 over 0. That doesn't work. The main tool that we have to evaluate a limit is to factor out the top and bottom and see if we can get something to cancel. Hopefully an x minus 3 factor, so that now we can plug in 3. And if I do factor the top and factor the bottom, on top I get x minus 2 times x minus 3. And on the bottom, I would get x plus 1 times x minus 3. Agreed? Good. Then I can cancel the x minus 3's and say that this is the same as the limit as x approaches 3 of x minus 2 over x plus 1. And now I can plug in 3. 3 minus 2 over 3 plus 1. And I get 1/4. Questions on that? Is that coming back, ringing a bell? Look familiar? It should. All right. Here's what our new rule would be able to do. We're going to get 1/4 again, but we're going to get it a different way. We're going to get it using this rule. Since we get an indeterminate form, since the top and the bottom are both differentiable, we're going to be able to use this rule. This time, we're going to take derivative of the top, and we're going to take derivative of the bottom. Derivative of x squared minus 5x plus 6 is 2x minus 5. Derivative of x squared minus 2x minus 3 is 2x minus 2. So took derivative of the top. I took derivative of the bottom. So now I should be able to plug in 3. Oh, and let's see what we get. 2 times 3, that's going to be 6 minus 5 is 1. And then 2 times 3, there we go. Put in 2 instead of 3. 2 times 3 on the bottom here is 6, and 6 minus 2 is 4, and we get 1/4. It's the same thing. So this is another tool that we have to take limits and be using limits. So there are some problems where, yes, we can do our factoring and canceling, but we can also use this rule as another way that we can take this limit. Now, if I look at that first problem, number 1, we're going to start by checking our 2 requirements to be able to use L'Hopital's rule. Thing number one we're going to check. This is f of x. This is my top. And then this is my bottom. So we need to check each of these around the point that we're trying to find the limit at. And make sure that we can do it this way. What we're looking for is that our limit at the top would make an indeterminate form, and our limit at the bottom would make an indeterminate form. So we write that the limit as x approaches infinity of natural log of x. As I get closer to infinity, well, as x gets larger and larger and larger, what's going to happen to natural log of x? As I get larger and larger and larger, the natural log of a number is also going to get larger and larger and larger, and closer and closer and closer to infinity. Then I need to check separately the limit of the bottom. As x gets larger and larger and larger, 2x also gets larger and larger and larger. Now, we do have a technique to find this limit from here. Okay, but I'm actually going to use L'Hopital's rule here, because this worksheet, this problem is going to say if we can use L'Hopital's rule, then we should use it. If we can't use it, then we should explain why not, which of these requirements is not satisfied, and then use some other way to find the limit. That's what we're going to do. So what our indeterminate form is an infinity over infinity. F and g are both differentiable. Natural log of x, we can take the derivative. For large values that are close to infinity, we sure can. Not for negative values, but for large values, since we're interested in the limit as we approach infinity. And then 2x is definitely differentiable. So we have f of g are both differentiable, and we've also checked this. So requirement number 2 is that f and g are both differentiable. We have said that f and g are both differentiable. Therefore, L'Hopital's rule can be used. So if we're using this rule for a problem, we need to check these two things. Check the limit at the top, check the limit at the bottom, and then say they're both differentiable. Then what that means is that the limit as x approaches infinity of the natural log of x over 2x equals the limit of derivative of the top over derivative of the bottom. Derivative of the top over derivative of the bottom. Derivative of natural log of x, 1 over x. Bottom, derivative of 2x is 2, which I can simplify one over x all over 2. Dividing by 2 is the same as multiplying by 1/2. So I'm taking 1 over x, I'm multiplying by 1 over 2, so that's going to, if I can rewrite this all as a 1 over 2x. And 1 over 2x, as x gets really, really, really big, this is going to get closer and closer and closer to 0. Because I'm going to get 1 over a really big number, which is going to be really tiny. And our way that we can do that on with the base problem is, I like to call it a race to infinity. On top, I have natural log of x. On bottom, I have 2x. Who wins? 2x wins over natural log of x. Because here's what those two graphs look like. Here's 2x, here's natural log of x. And natural log of x is growing at a lot slower pace, and then here's 2x. So this way was saying, like, how long until I get to 20? I only need to hit 10 to get to 20. Natural log of x takes a lot longer to get to 20. And that's only going to get a greater difference as I get larger and larger and larger. So that's my race to infinity. I would get the same answer since the top is growing a lot slower than the bottom. Then eventually, as I get larger and larger and larger, I'm going to get a pretty big number over a really big number, and that's going to get closer and closer to 0. But I can also use this derivative of the top over derivative of the bottom rule. Let's do a couple more. This is number 4. Here's f, here's g. So thing number 1 we need to do is we need to take the limit of f, take the limit of the top, take the limit of the bottom, and make sure that we have an indeterminate form. We're approaching -1 of, well, let's plug in -1. Hey, it's 0. Take the limit of the bottom. Natural log of x squared. And natural log of 1 is 0. So I have the top is 0, I have the bottom is 0. There's my indeterminate form. So at the points around -1, well, the only place natural log is not differentiable for here, since we can put in negative numbers, because they're going to get squared. The only place we have to worry about is 0. Luckily, we're not trying to find around 0, we're trying to find around -1. So there's requirement number 1. And then requirement number 2 is f and g are differentiable around -1. So L'Hopital's rule can be used. So that's good news. We can do this by doing derivative of the top over derivative of the bottom. Let's do it. Derivative of x squared minus 1 is 2x. That was easy. Derivative natural log of x squared. Over x squared. What? It's 1 over x squared, isn't it?
Yeah, I'm sure it is, Mr. Hall.
Why are you doubting me?
I'm not doubting you.
Do you think I'm forgetting something?
No, you could never things. We don't forget things in this class.
You think I might be forgetting the
chain
chain rule? Derivative of the inside part. Derivative of x squared. It's 2x. I can cancel my 2x's here and say this is the same thing as the limit as x approaches -1 of 1 over x squared. One over x squared is x squared. And now I can just plug in -1. The answer is 1. And this one, with the other ones, I said there's another way we know how to find this limit. This one, we have to use this rule to find a limit. There's not another way to do it. Because you can't get any factors that cancel. You can't do any of that stuff. You would have to use this limit. Derivative of the top over derivative of the bottom. Questions on that? Okay, we're going to look at one more today. Limit as x approaches 1 from the right. Oh, these are pretty much the same function, so I'm going to say they're differentiable. Both of these are differentiable. And then let's go ahead and check our requirements. I'm trying to stay away from saying conditions because I don't want to make the stats kids upset at me. So, checking these two requirements. We need to check the limit as x approaches 1 of x squared. And we need to check the limit as x approaches 1 from the right. Of natural log of x squared. And again, what we need to check for is that we have both of them having an indeterminate form. Down here, I can plug in and get natural log of 1, and as we saw in the last problem, natural log of 1 is 0. And then over here, we get 1 squared is 1. Oh no. That's not 0. That's not an infinity. That's not an indeterminate form. So that means we cannot use this rule to do the limit. So we are going to say, since this is not an indeterminate form, Close enough. Oh. There we go. That's what the problem was. I was like, I'm pretty sure that's right. Okay. The vowels are not my problem. Since this is not an indeterminate form, we cannot use L'Hopital's rule. So that means that you will have to come up with some other strategy to find this limit. And what you should do is we are coming at this from the right. So that means we need to think about what would happen if I plugged in 1.01 and 1.00001. This one's getting closer to 1. This one's getting closer to 0. So the question you have to answer is, from which direction am I getting closer and closer to 0? From the positive direction or from the negative direction? And that should tell me what that limit is.